Hi everybody, in this recording we'll be going over section 3.1, Extrema on an interval. Our goal is that by the end of this presentation you'll be able to understand the definition of extrema of a function on an interval, understand the definition of relative extrema of a function on an open interval, and you'll be able to find extrema on a closed interval. In calculus, it is very important to determine the behavior of a function f on an interval I. So this will allow us to know if a function has a maximum or a minimum value, and where that function will be increasing or decreasing. So in this chapter, you'll be able to use derivatives to determine the behavior of a function f on an interval I. And you'll also be able to learn how to use derivatives in real-life problems. So for our examples here, at the far left, we have a function f, and it is continuous on a closed interval (1, 2). So the closed interval means that the endpoints are included. And because of that, this function f of x is equal to x squared plus 1, it will have a maximum at the point 2, 5, because that point is included. It also has a minimum at the point 0, 1, because that is the lowest point, and because f is continuous right there. For the next example, we have f is continuous on an open interval. So f is defined as x squared plus 1, but since it's an open interval, the endpoints, (1 and 2, are not included. So therefore, that point 2, 5 is not a maximum because that point is not in the interval. But the minimum is in the interval and it is the minimum value. So this function does have a minimum. For our last example, we have a function g, and it is a piecewise function. So it is defined as x squared plus 1, where x is not equal to 0, and g of x is equal to 2 when x is equal to 0. So we see at the point 0, we have a discontinuity. We have it is equal to 2, and it is also equal to 1. So therefore, that point is not a minimum because we have two different values. But it does have a maximum at the point 2, 5 because it is on a closed interval, so the endpoints are included, and that is a max. Here we have the definition of extrema. So if we let f be a function defined on the interval I containing a constant c, then f of c is the minimum of f on the interval I when f of c is less than or equal to f of x for all the x in the interval I. Now for the maximum, f of c is the maximum of f on the interval I when f of c is greater than or equal to f of x for all the x in that interval I. So the minimum and maximum of a function on an interval are the extreme values, or extrema, of the function on the interval. The minimum and the maximum of a function on an interval are also known as absolute minimum and absolute maximum, or the global minimum and global maximum. This can happen at interior points or at endpoints. If the extrema are at the endpoints, then it is called an endpoint extrema. Now we have theorem 3.1, the extreme value theorem. So this states that if f is a continuous function on a closed interval a, b, then f has both a minimum and a maximum on that interval. So those minimum and maximum are guaranteed if f is continuous on that closed interval. Now we have relative extrema. So if there's an open interval containing c, on which f of c is a maximum, then f of c is called a relative maximum of f. Or you can state that the function f has a relative maximum at the point c, f of c. Now if there is an open interval containing c, which f of c is a minimum, then f of c is called a relative minimum. Or similarly, you can state that f has a relative minimum at the point c, f of c. The plural of relative maximum is relative maxima, and the plural of relative minimum is relative minima. Relative maximum and relative minimum are also known as the local maximum and local minimum. Here we have some examples of finding the relative extrema graphically. So for our first example, a, we have the function f of x is equal to 4x divided by x squared plus 4. We see that for the graph of a, we have a relative maximum at the point 2, 1. Now for example b, we have the function f of x is equal to the absolute value of x minus 1. From the graph of b, we see that the function f of x has a relative and an absolute minimum at the point 1, 0. Now for the function in example c, we have f of x is equal to the cosine of x. Now that one will have a relative minimum at the point pi, (-1), and it will have a relative maximum at the point 2 pi, 1. Now we'll be computing our relative extrema using our derivatives. So for the first example, we have the function f of x is equal to 4x divided by x squared plus 4. And we got the relative extrema 2, 1. Now how did we get that? First, we computed the derivative of f of x. Since our function is a rational function, we'll be using the quotient rule. So that is how we got f prime of x is equal to 16 minus 4x squared divided by x squared plus 4 squared. Now, to find our relative extrema, we will set the derivative equal to 0. In our case, that will yield x is equal to 2 in the interval that we are looking at. So just to double check that that is the value of the relative maximum, we plug in 2 into our derivative, so f prime of 2, and that gives us 0. So that checks out. Now to find the y value of our relative extrema, we will plug in our x value, 2, into our original function. So we'll do f of 2, and that yields 1. So that is how we got the coordinate 2, 1 for our relative extrema. Now for our second example, f of x is equal to the absolute value of x minus 1. We do the same thing, we take the derivative. So that yields f prime of x is equal to negative 1 for x less than 1, and positive 1 for x greater than 1. We can take the limit as x approaches 1 from the left-hand side, and that'll yield negative 1. And we'll take the limit as x approaches 1 from the right-hand side, and that'll yield positive 1. So since the values do not match, f prime of 1 does not exist. But x is equal to 1 is still a critical point because we had a sharp turn in the absolute value function. So plugging in 1 in our original function, f of 1, we get f of 1 is equal to 0. So we stated that a local minimum occurs when f of c is less than or equal to f of x for all x in the interval that we were looking at. For our case, f of c is equal to 0, and 0 is less than or equal to f of x for all of the x inside of that interval. So therefore, our relative extrema, or in our case, the absolute minimum, happened at the point 1, 0. Now we have our last example, part c, where f of x is equal to cosine of x. We repeat the process and compute the derivative. So f prime of x is equal to negative sine of x. We set that equal to 0, and on the interval that we're looking at, negative sine of x set equal to 0 occurs when x is equal to pi, and when x is equal to 2 pi. Now plugging in pi into our original function, f of x, will yield cosine of pi, and that is equal to negative 1. So for our relative minimum, we have the point pi, negative 1. Now plugging in 2 pi into our original function, f of x, we have cosine of 2 pi, and that is equal to positive 1. So that is how we got the point 2 pi, 1 for our relative maximum. There are cases that the derivative of the relative extremum is either 0 or does not exist. The x values are special points called critical numbers. We saw that happen in our previous example, or one of our previous examples, part b, when we had the function f of x is equal to the absolute value of x minus 1. We saw that x is equal to 1 was a critical number, but the derivative did not exist at that point because we had a sharp turn. Now for the definition of a critical number. Let f be defined at c. If f prime of c is equal to 0, or if f is not differentiable at c, then c is a critical number of f. Now here's an important thing to note. The critical number c has to be in the domain of f, but c does not have to be in the domain of f prime. Now for theorem 3.2, we have the relative extrema occur only at critical numbers. So this theorem states that if f has a relative minimum or a relative maximum at x is equal to c, then c is a critical number of f. Now over to the right, we have some graphical examples of c being a critical number. So for the first one on the right-hand side, the first one where we have a sharp turn, f prime of c does not exist because it has a sharp turn. For the second one, we have f prime of c is equal to 0. We have a horizontal tangent. So based on the theorem 3.2, you can use the following guidelines to find the extrema on a closed interval. So the first guideline is find the critical numbers of f in the open interval ab. Evaluate f at each critical number in the open interval ab. Evaluate f at each endpoint of the closed interval ab. The least of these values is the minimum. The greatest is the maximum. Here we have an example of finding the extrema on a closed interval. So we're given the function f of x is equal to 3x to the power of 4 minus 8x cubed on the closed interval -1, 3. So the first step was to find the derivative of the function. So using the exponent rule, we have f prime of x is equal to 12x cubed minus 24x squared. Now we find all the values for which f prime of x is equal to 0 or does not exist. So we just set our derivative equal to 0. So 12x cubed minus 24x squared is equal to 0. We can factor out a 12x squared, so we'll have 12x squared times x minus 2 equal to 0. Setting each of those equal to 0, we have that x is equal to 0 and 2. So that means our two critical points are at x is equal to 0 and at 2. Looking at our graph, we see that we have a horizontal tangent line when x is equal to 0, so at the origin, 0, 0, and at the point 2, negative 16. Now we can make a table evaluating our critical points and our endpoints of the interval. So we were given the interval -1, 3, so we will be evaluating f of -1 and f of 3. And we computed our critical numbers, which were 0 and 2. So we will be evaluating f of 0 and f of 2. So f of -1 is equal to 11, f of 0 is equal to 0, f of 2 is equal to negative 16, and f of 3 is equal to 27. So we make sure that we evaluate the original function, not the derivative. Here we saw that we plugged in our endpoints and our critical numbers into our original f of x. So by comparing the y values from the table, we can conclude that the absolute maximum is 27 because that is our greatest y value. Now the absolute minimum is at y is equal to negative 16, which was at our critical point x is equal to 2.